Okay, so just to quickly run through a couple of things from this question. Um, if we have a look at from exercise 17.3, question 5. So write down the coordinates of the points where the curve and line meet. So what we're talking about here is the points that you can see where the intersections occur. Okay, so one point is 3, 9, and the other point is minus 1, 1. Okay, so they're the coordinates of where the curve and line meet. So then the next part of this actually is getting you to look at, you can see you've got the curve, the red curve, and you've got the straight line, and they're asking you to solve the equation where the two are equal to each other. So the two are equal to each other when the two intersect. So the points I've just highlighted there, 3, 9 and minus 1, 1, are the 2 points where they meet. It is the solution to the two equations equaling to each other, f of x being equal to g of x. Okay, and actually in part 4, it asks again about f of x equaling g of x. Okay, so I suppose you need to appreciate the idea that both in part 1, part 2, and part 4, they're talking about, and actually part 3 as well. The whole thing is about the first 4 parts is about the ideas of those two graphs intersecting. The intersections of graphs are when the two functions are the same, is when the two algebraic expressions are the same, is when the two names f of x and g of x are the same. Okay, so they're all interconnected. The key idea is intersections of graphs, equality of functions, however which way it's written. Okay, so in terms of a solution, when we consider the fact that minus 1, 1 and 3, 9 are the intersections, the values of x, which is in a sense the solution, okay, the solution for part 2 is x is minus 1 and x is 3. They are the solutions to that. Okay, the solutions to fx equals g of x, they're the solutions of x squared being equal to 2x plus 3. Okay, the coordinates of the intersections are the two, the x and y's of any intersections. Now, eventually, lastly, the last part, use the graph to find the range of values of x for which f of x is less than g of x. So fx is the curve, okay, it's the red curve. G of x is the blue straight line. So when is the curve? Now, when it's less than, it means below. So when is the curve f of x, below g of x, the line? Well, you can see that occurs in a sense, I suppose, in this section here. That's where the curve is below the straight line. So for the last part there, the key idea we're actually putting forward is that between the values of minus 1 and 3, so when x is between minus 1 and 3, okay, in those sections, in between that section, that is when f of x is going to be less than g of x, when the curve is below the straight line. Question 6 is throwing you a couple of graphs there with two functions, and the first part here, 3x minus x squared. Well, that's this one here, okay? So when is that curve equal to 0? Well, you can see it's equal to 0 when f of x is equal to 0. Okay, when the function is equal to 0, when y is equal to 0, it's when it crosses the x-axis. Okay, function equals 0, intersections. Okay, so for this one here, we're saying the values of 0 and 3 meet that solution. Okay. Next part, and actually before we go on, let's stick with this particular graph. If we're then asked about 3x minus x squared is equal to minus 3, what we're talking about here is using the same graph. Where's minus 3? So there's minus 3. So what are the solutions? When does the graph intersect that point? Okay, when is the function? So this is a bit like this first one was a bit like f of x is equal to naught. Okay, you're finding the x-axis intercepts. When this one here is a bit like saying, well, it's a function equal to a constant. That's why we're drawing the horizontal line. Okay, and so what are the solutions? Well, you have to read off x values. So let's just say, for sake of argument, we'll estimate it's 0.8. Minus 0.8, should I say, and we'll estimate that it's 3.8. Okay. You might come up with 3.9 or 3.75. You know, there's a number of different sort of, I suppose, answers that could be come up with. Okay. So the other two questions are about the other graph. Okay. So we've got x squared minus 3x minus 4. Okay, so in both these two cases, we're looking at this first graph. So when is x squared minus 3x minus 4 equal to naught? So again, that occurs when we've got the intersection with the x-axis. So very quickly, we've got x being minus 1 and x being 4. They're the two intersections. And then the function equal to minus 2. So again, it's a bit like this idea of a function equal to a constant. You draw your horizontal line across. Where are the intersections? And you read off values, okay, of the x-axis. So we get x is equal to what's about minus a half, and it's about 3.5. And again, you know, the back of the book says 3.6 and minus 0.6, so not far off. You'd certainly, you know, I'm reading off the values. I don't see why my answers are only better or worse than the correct answers. Question 8 again is reading off of a graph that's been given to you. X plus 2 all squared. So when is that function equal to naught? Okay, so function equal to naught means the x-axis intercept. So there's only one solution in this instance, and that is x being equal to minus 2. Did you get one or two values for x? We got one. In a sense, we've got a repeated root. It's the technical name for it, but the reality is it's just one. If you got one value only, the value of x that you found is called a repeated root. Explain how the graph reflects this repeated root. Well, I suppose the graph reflects it by the fact it bounces off. Okay, it doesn't appear anywhere else. Okay, that's not what it's hinting at. In terms of why it is repeated, okay, it goes back to the algebra in the fact that you've got a function that has been squared, i.e. what you have is you have x plus 2 multiplied by itself. So that's where you get the repeat. You get the repeat from the fact you've got two factors that are the same. Okay, you get minus 2 from this when x plus 2 equals naught. You get minus 2, but also when this one is equal to naught, you get x is equal to minus 2. That's why it's repeated, okay, because you've got a factor that is repeated. Question 9 is straightforward if you remember the key way of going through this. So I'm interested in, and I'm always interested in, where a graph crosses the y-axis. So we can see there's one that crosses at minus 2, there's another one that crosses at 3, and there's another one that crosses somewhere up here. We have no idea whether it's 7, 8, 9, 10, or whatever. Okay, but if we then look at the functions, you see there's one function that's got a constant inside it, x squared plus x minus 2. Okay, which is the same as this minus 2 down here. So that's that graph there. So we can say this a, okay, is this first function. And then the next function we've got here, we've got one that has a plus 9. Okay, and we can see, well, hang on a second, C seems to sort of do that, possibly. Okay, so we can say that the second one is C, and just to double check, we should find that the last one is going to be B. Well, let's have a look at this. We've got the plus 3 there, So that works. Okay, that fits. So that must be B. All I'm doing is looking at the constant. Okay, I'm not worrying about all the rest of the governs with it. The constant is where it crosses the y-axis. So it hasn't taken me very long. I haven't done do any substitution or any solving algebra. I'm just looking at the structure. Okay, which function has a repeated root? Well, that's the one that bounces off the x-axis, like I mentioned in the, I think, the previous question of this video. So here we've got a repeated root because it bounces off. Okay, so that's C. So C has a repeated root. And then lastly, use the graph to solve the equation. So you've got one function is equal to another function here, okay? And you can see that what you've got is this first one here, that refers to A, okay? And A is this function, this first function here, this one here, okay? The second one, x squared minus 6x plus 9, okay, that's C, okay, as a function. And you can see C there, okay. So when are they equal to each other? They are equal to each other when you've got an intersection, and that intersection occurs, I'm running out of colours here, at that point there. There's no other intersection than that point. So there's not a lot going on this graph, okay, because you've got three curves intersecting along with the axes. But you have to, I'm using the highlighters to try and make me understand what's going on. So if I look at between these two curves, I get an intersection here in the middle, okay. So read off of that value. Now it's not an easy answer. It looks about 1.5. Oh, wrong sort of pen. So it looks as though we've got approximately a value of x being 1.5, and the y value looks, so it's a little bit more. It's about 2, or maybe more than 2. I'm willing to suggest it's 2. So let's just go with the coordinates of 1.5, comma. My pen is playing silly buggers on me. Doesn't want to write. Okay, there you go. There's the coordinates. Okay, the solution is, sorry, it was your y is equal to 2. The solution is 1.5. Okay, that's the actual sort of answer to the question. That's the value that works. There are other ways of doing it. You can sit and try and solve the equation. Okay, so it says to use the graph to solve the equation. I could use algebra. That's the answer to question 9.